Alright, in this video I want to talk about the finite rectangular well solutions for the Schrodinger equation. And I don't want to spend too much time on this because these sort of rectangular well solutions they don't have any real, I guess, physical sort of meaning. They're supposed to just be illustrative of solutions to the Schrodinger equation, and the finite rectangular well is illustrative of the differences from the infinite rectangular well, potential well. I should clarify that it's the potential energy well. And what's illustrative for this one is the differences that it has, and I will point out that the two main differences. The first one is that the wave function psi is not equal to zero at at the boundaries. And the second difference that the finite version is supposed to be illustrative of is that if the energy of your system, that actually looks kind of like a summation, it's an E, if the energy is less than the potential, then the particle is bound to your system. It's bound into your potential well. But if the energy is greater than the potential, which was sort of impossible when we have infinite potential. But in this case, since we have finite, this can be the case, and this will mean that the particle is free, essentially that it can escape your well. And so these are, like I said, these are the differences between the finite and infinite rectangular potential wells. And that's essentially what the finite version of the rectangular potential well is supposed to sort of show, is that these two things, so like I said, the rectangular wells are not actual physical systems, but these two things are true of actual systems, which you will not find in the infinite rectangular well. But essentially what this means is, so I have this written here, or drawn here, and this is a finite rectangular well, so we would say that on both sides that v is not equal to infinity, or I guess we could say that v is less than infinity on both sides here. And so what that means is that our wave functions here do not go to zero at the edges here. So this should probably actually, so it would look more like this. So it'll sort of, it goes to zero as you sort of get further away, but it doesn't start at zero. So this will sort of decay down to zero. This will decay down to zero. This will decay down to zero. But what we're interested in is right here at the edges where where we go from being in the zero potential here into this finite potential here. And so these right here are not zero. So if you remember from the infinite rectangular well, we had a well that was like this, where v was equal to infinity, and we had to have it go to zero on both sides so that we knew that it went to zero. The wave function went to zero at the edges, but here that is not the case. And so what we need essentially is that that these be continuous between the area where there is no potential and the area where there is potential. So right here at the edge, what we need is for our the wave function on the outside, well, in the potential and in the well to be equal to each other. And so we need the wave function, so we can say maybe inside, so inside the well here, to be equal to the wave function on the outside right here at the boundaries. And we also need it to be the case that the derivative, so we'll just say dx here of in is also equal to dx of out, because we need the slope, the instantaneous slope right at the boundaries to be the same. And so this is sort of showing the so I have it marked off as section 1 in Roman numerals, section 2 and section 3, and this, which is an image taken right from the book that I've been following for this, the Student's Guide to the Schrodinger Equation by Daniel A. Fleisch. And so this is telling us that in section 1 we have this c, this constant times e to this is a kappa x, and so that is our decay over here where we're in the negative. So in here the kappa would be negative, and so this would be an exponential decay, and then this is the partial derivative of it, of this c to the ekx here, or kappa rather, and so this is also negative, and so we see that that's going down right here. Then inside we have our usual sine or cosine function, so it has the oscillation. We see that it says here that it's oscillatory. And then on the right side we have the e to the minus kappa here, which is telling us that outside this we need an exponential decay, and that's why I sort of tried to redraw this so that they're exponential decays on the outside, or within the potential energy here. And so we know from before that, so inside the well where there is no potential, as I said, the wave function is going to take on the form of, so a general solution will be something like cosine, and we then have our kx. So we're using k instead of kappa when we're within the well here. So it'll be a cosine kx plus b sine of kx within the well. And so we know that from our previous videos that k is equal to 2m over h bar squared e minus v, and then that is all square root. But we know inside the well, and it doesn't have to be the case, but in this illustrative purpose we say that we have no potential, and so this simplifies to 2m over h bar squared e. And so then we know that k is it's proportional to energy, so we can say that k is proportional to energy, to the energy of our particle. And then we know from right here and from the previous video that on the outside, so we'll call this inside, we'll say that psi outside, so when we're within the potential, then we have a solution, a general solution that will look like c e to the kappa, and I can't really draw kappa, so I just use a capital K rather than the lowercase k here. So kappa x, and then plus d e to the minus kappa x. So this is a general solution when we are when we are outside. And we know that that on the right side of it here that this C is going to be that if this is not 0, then this is going to go to infinity. This is this e to the kappa x is going to keep growing exponentially. So on the right side, we have the boundary condition that C has to be equal to 0. And then we have D. In the book, I think it goes through a little bit of math to try and get it so that that D is just equal to minus C, and so we can say that D is equal to minus C, and so that's why up here it has this. But anyway, the idea is that on the right side, when we have the positive kappa here, then we need this to be 0, and on the left side, then we have minus C with the minus kappa here, and so that goes to 0 on the right side. But anyway, the takeaway here is that we have our kappa, which, as I said, I'm using this sort of capital K because I can't really script it so that it looks like a kappa instead of a K like it has here. So I'm just using an uppercase K, is going to be equal to 2m over h bar squared. And then this will actually be v minus e. Then we do the square root. But since the energy is not changing here, then we say that kappa is going to be proportional to our v here. But anyway, so if we have a larger v, then we have a faster decay, which we can see here. If our kappa is larger, then we're going to have this faster decay. So as we know, when we go to the limit where v is infinity, then the decay is, I guess you could say, instantaneously. It's 0 right at the boundary, whereas if v is less than infinity, then we're going to have a decay that's not instantaneous, so it's not going to be 0 at the boundary, but it's going to decay. But if that v keeps getting larger and larger, then that decay will keep getting sort of larger and larger until you get to that point where it just goes right to 0 at the boundary when v is infinity. And so our K, or kappa, or uppercase K or kappa here, is proportional to V. So as V gets larger, our K gets larger, and that makes the decay occur more rapidly. And so, as I said, we wanted it to be the case that that psi inside and psi outside are equal, and the first derivative of psi inside and psi outside are equal at the boundary. And so I've drawn here, I have the boundaries at minus a over 2 and a over 2, and so the total length of it, the total length of it is equal to a. We just have half of it on the positive side of 0 and half on the negative side of 0. So what we want, though, is we want our C e to the kappa minus a over 2. So that's this is where x is equal to minus a over 2. And we want that to be equal to a cosine of k, so our lowercase k here, minus a over 2. And so this is saying, like I said, that we want on the left side for at the instantaneous point here at where we go from no potential to some potential, some finite potential, to be equal. So we want this to be equal, and we could say the same thing for the right side where we have positive a over 2. And then we also want our first derivative, which is our kappa c e to the kappa minus a over 2. And like I said, this will be the same thing on the positive a over 2 side. I'm just not going to write that out. And that will be equal to minus k a sine of k minus a over 2. And so this is the first derivative of the cosine here, and this is the first derivative of this right here. So we want these two things to be true. And then what we do is we take what's called the logarithmic derivative, which is we essentially just take the derivative and divide it by the function here. And so what we end up with is we end up with our kappa here, c e to the kappa minus a over 2, and we divide that by the c e to the kappa minus a over 2. Then we set that equal to minus k a sine of k times minus a over 2 divided by, then we have our a cosine of square bracket k minus a over 2. And so this is what's called the logarithmic derivative. And I'm not going to go through all the sort of algebra and so forth, but what we end up with is we end up with something that looks like our kappa equals minus k tangent of minus k a over 2, which this is just also equal to the positive. So positive k tangent of positive k a over 2. And then we just divide both sides by the k. And I will actually move up for this just for the sake of room. And so we have our kappa divided by k is equal to the tangent of the k a over 2. And so we end up with this equation right here, and this like I said, we're attempting to look for where it is the case, and I had this image here. This is just to sort of show that we need a specific sort of k and kappa here in order for this to be continuous at the boundaries. If we have too much energy in the k, then we have this high curvature, and we end up having these discontinuities or these mismatches here. Or if we have sort of the k, or the larger v naught minus e means larger kappa here. And so this is essentially just showing that, like I said, we need this match at the boundaries here, and that's what our equation is trying to do. Remember, we did the logarithmic derivative of the function or of the derivative at the boundaries divided by the function at the boundaries, which we wanted those to be equal. And through that, we ended up getting this equation right here. And so this is what they call a transcendental equation, because we have this tangent here. And so that makes it difficult to solve analytically. And so what you can do is you can either try to solve it numerically, which is sort of a trial and error thing, or you can try solving it graphically. And so what you do is you plot kappa over k for some specific kappa, because remember our kappa is dependent on our potential here, and k is dependent on the energy here. And so we want to find for a specific potential what the energy levels of our particle are going to be. And so we are varying the k, well, for a specific kappa, for a specific potential. So we plot that, and then we also plot the tangent of the different k's, the different energies for A, which remember A is the length of our potential well. So as I said, A is the length, and we just have it split into the two halves here. And so, I'll show later on that we could actually vary A, and that will give us different energies. But the takeaway point here, as I said, we are using a specific kappa, a specific potential, and we are varying k, which is proportional to the energy. So as we vary k here on the left side, we will end up with a function that sort of goes down, because as the denominator gets larger, our function will get smaller. And then here we are also doing it as a function of k, and so we will have a tangent function with k. And so that's what these graphs here are about. So these are solutions for different. So the solid lines here are the solution. Well, it's the kappa over k for different kappas. So this line here is one specific kappa with as a function of k here. So k is what is varying. And so the kappa for this one, for instance, is for a potential of 60 electron volts. This one is for 2 electron volts. This one is for 160 electron volts. And then these dotted lines are the tangent function. So the tangents as a function of k. And so what we're looking for is the places where these intersect. Because remember, as I said, what we're looking for is where the function inside and the function outside and the derivatives are equal to each other. And so we are looking for where these intersect. So we want them to have the same value. So we want these to intersect. And so as I said, the k is proportional to the energy. So we say that k, well, it's actually equal to the 2m over h bar squared e, and that's the square root. And so if we just square these and sort of rearrange it, we have that e is equal to h bar squared k squared over 2m. And from the infinite rectangular well, we know that that the k was was n pi over a, and so we can say that this for the infinite. So maybe we'll put a little superscript infinity here was equal to. So we have k squared here, so it's n squared pi squared h bar squared over 2m a squared. And we know from the infinite square well that if we take the energy level where n equals 1, then what we end up getting, so we'll say that E for the infinite square well with energy level of 1 was equal to 6.02 electron volts. So I'm not going to go through all the calculations, but this is what we would get for the first energy level. And so if we then do the E, the energy, I guess for the 160 electron volt potential, so instead of infinity, we will say that this is, say, the 160 electron volt at 1. Then what we end up getting, so then we have to look at the graph here. And so we see at the first energy level here is about 0.445 pi, so the Ka over 2 is 0.445 pi, and so that goes up to here, and then we go over here, and that ends up being about 4.76 electron volts. So 4.76 electron volts. 6 electron volts from what we have here. And so we see that this is lower than what we have for the infinite potential well. I think it's in the book. I think it actually takes it rounds this up to 4.8 and then 6.02, and that ended up being something like 0.8. So the ratio, and as we went up different levels. So I think if it was this, so if we had the E for 160 electron volts, 2 divided by that, it was something closer like 0.78. But anyway, we see that that it's smaller for these in the finite rectangular well. Also, one thing to sort of point out as well is that in the finite rectangular well, we do have a finite number of these solutions here, and so we see what that ends up meaning is that if we have an energy level that goes higher than this, then that will actually cause the electron to escape the well, and so like in the infinite rectangular, well, we essentially allowed n. So we had En, where the n is the energy levels. We essentially said that this could go to infinity. That n that we could have n go to infinity, whereas in this the n cannot go to infinity, and we can actually find out sort of what the highest energy level can be. And so if we take this equation here, and instead of using these k squared, we instead substitute in what we are actually using, which is the Ka over 2, and square that. So this video is already getting a little long. I'm not going to run through the all the calculations, but what we will get is we will have E equals h bar squared, and we have Ka over 2 squared, and then we have to have the 2 over A squared there. So we're just substituting all this in here for the K squared rather, the K squared from this equation over here, since we're using this Ka over 2 rather than K, and then we do that over 2m, and this can then simplify down to so 2, because 2 squared divided by 2 is or 2 squared is 4 divided by 2, so we have 2h bar squared Ka over 2 squared over ma squared. Remember, a in this case is the width of our well here. And so if we plug in sort of the highest here, which is 3 pi, and then we use for the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms, and then we see for this we see that our A, I don't think it has it on here, but I do have it written down here. So in the book they were using A of 2.5 times 10 to the negative 10 meters. So that's on the like 2.5 angstrom scale. And then we use the Ka over 2 as 3 pi, which as we see is our highest right here. So essentially what we end up getting is that let's see, I think I have it written down here. Yeah, so that E will end up being equal to 216.6 electron volts. And essentially what I'm showing here is that this is sort of the highest energy level that you could get to for our system with our finite well at 160 electron volts. And so we see that this is, that right here is, we ended up with about 114.3 electron volts there. So that is the highest energy level. The next highest energy level would be above this 216.6 electron volts. And so the electron would actually become free of the system. It would escape the well and no longer be bound to our system. And so this is the graph here where instead of varying K in the tangent, they're varying the A, which is the width of the well. So we see here, this is A at 2.5 times 10 to the negative 10 meters here, and then A is 10 times 10 to the negative 10, and then 25 times 10 to the negative 10. So with K being held constant, but changing the A, changing the width of the well, we can still graph it that way and end up getting different solutions. So there will be different energies depending on the width of the well here, and so we can kind of do the same procedure here, but we're just changing the width of the well rather than the K, rather than the energy of our particle. Yeah, and so these are just sort of what the solutions will look like. And one thing to notice here, we do have this even and odd parity. So what's called uh, parity. And even just means that it's the same on both sides of the zero here, and odd just means that it is sort of equal magnitude but opposite sign on the different sides here. And that will actually become something a little bit more important when we actually get to sort of real system, sort of 3D solutions uh, to the Schrodinger equation, when we start ending up using sort of the solutions that use things like the Bessel functions and the Hermite functions and stuff, which gets us into the idea of of having orthogonal functions. So you may have heard of orthogonality in terms of, so if we have two lines here that are perpendicular, we say they're orthogonal. In vectors, we say that if we have orthogonal vectors, that if we take the inner product or dot product of them, that it equals zero. Uh, and I'm probably going to, before I get to solutions of the Schrodinger equation in sort of real systems, do a few videos on ideas of things like orthogonal functions. So that's if you take the integral of some function. So we'll say that this is fn and fm x, that this equals 0 if n is not equal to m. But anyway, I'm getting a little bit ahead of ourselves here. So the main takeaway at this point, as I said, is that that our wave function is not equal to 0. I guess I should have put a 0 in here, is not equal to 0 at the boundaries, and that we can only have a certain number of energy levels, because once the energy gets higher than the potential, then our particle becomes free. So the particle becomes free. And so we saw that here with this, that we have our right here, that we want our function at the edges to be equal. So the function in the potential or outside the well equal to the function inside the well at the two edges, and we want the first derivatives to be equal to each other at the edges. So that was this first thing here, and then the second thing, which I went over in a little bit more of a hurry, I think, but that was essentially this idea over here that there's this sort of maximum energy that if the energy of our particle exceeds this, then it will escape the well. And so those are sort of the two take-home messages from this video, is that, as I've said, the function is not 0 at the boundaries, and if the energy is below the potential here, that the particle is bound. If it's above, then the particle becomes free. And so in the next video, I am going to go into the somewhat more realistic, but still not realistic, because we're still talking in one dimension. We're still talking in one dimensional here, but we will talk about what's called the harmonic oscillator. And so that is a potential that, instead of being like this, is more like this. And so you can see, can draw that up maybe a little bit better. It's still symmetric. So it's something that looks maybe more like this. And so we would say that this maybe is the maximum energy of our potential. So only here at the very center is V equal to 0, and then we actually have it climbing sort of steadily on the outside rather than being this step function here where we go right from 0 potential to whatever the potential is on the outside. And so the lesson we learned in here is still going to apply in that if we have a particle in our potential here, that it will decay off to 0, but we still want it to the function and the first derivative to be equal at the sides here, and we will still take into account the lesson that if the energy is greater than the potential, then our particle can actually escape the well. And after I talk about this harmonic oscillator, then I will talk about a free particle. So that is a particle, essentially a particle where the particle energy is greater than the potential. So the potential doesn't necessarily have to be 0, but that would be a particular case of the energy of the particle being greater than the potential. But anyway, like I said, that is the next video where we'll talk about this harmonic oscillator potential. Then I'll talk a little bit about a one-dimensional free particle. Then after that, I am going to go a little bit into sort of more math before I get to the actual 3D solutions to the Schrodinger equation, which are obviously solutions that apply to actual physical systems in the real world. But the reason we do these one-dimensional cases, like I said, is just to sort of illustrate some of the principles that will still be present in these 3D solutions. But the 3D solutions, I will sort of warn here in advance, can get very complicated just as far as sort of the mathematical manipulations and even the concepts, which, as I said, is why I'm going to go into some of the properties of things like the orthogonal functions and the I think I think they're called the hypergeometric functions and things like that. So I'll go a little bit into those topics before I actually get into 3D solutions. But anyway, I'm sort of rambling now. I hope you found this video helpful, and I will see you in another video.